every single day. Your phone buzzes with news, your social media feed scrolls by, advertisements pop up. And even in casual conversations, you're just bombarded with data and claims constantly. And so often, these claims lean on numbers, right? Figures, to add credibility.
Yeah, they sound convincing.
But here's the real question. How do you truly know if you can trust them? How do you tell good reasoning from, well, faulty reasoning when these numbers are flying at you?
That's exactly what we're diving into today. This is kind of your shortcut to becoming a much smarter, more discerning consumer of statistical claims.
Yeah.
Our mission here is really to arm you with the tools to react intelligently to all that information you encounter, to help you, take control of your understanding of the world.
So we're digging into insights from online statistics education.
That's the plan. It's a really foundational text that shows us statistics are way more than just dry facts and figures.
Yeah, I think of it like this. Statistics, in the broadest sense, it's this powerful set of techniques, procedures for analyzing, interpreting, displaying.
And making decisions. That's key.
Right, making informed decisions based on data. So let's unpack that. Let's start with why this even matters to your everyday life.
Okay.
So let's kick things off by really getting why statistics are so crucial. Because honestly, learning to decipher data, it's a huge step towards gaining control over how you see the world.
Absolutely. If you can't tell solid reasoning from, let's say, questionable claims, you are vulnerable.
Vulnerable to manipulation, to making decisions that aren't really in your best interest.
Exactly. Think about some of the stuff you hear every day. Claims like women make 75 cents to every dollar a man makes for the same job.
Or that one about birthdays. An 80% chance in a room of 30 people to share a birthday.
Or the classic joke one, 79.48% of all statistics are made up on the spot.
Right.
But seriously, these claims, whether they're from psychology, health, sports, business, they're all inherently statistical.
And you mentioned ads earlier. Television advertisements seem like a prime example where numbers just get thrown around.
Oh, definitely. Often without careful analysis backing them up. They can be incredibly misleading, potentially push you into buying something you don't need based on some shaky percentage.
So learning how to evaluate these isn't just like academic.
No, not at all. It's a crucial life skill.
Okay, so how do we start sorting through all this? You said the world of statistics basically splits into two main branches.
That's right. Descriptive and inferential. Let's start with descriptive.
Okay, descriptive statistics. What is it, really? Why do we need it?
Well, descriptive stats are pretty much what they sound like. They're about describing what's right in front of you, summarizing, characterizing the data you have.
Without trying to generalize beyond that specific set of data.
Exactly. So imagine we're looking at salaries in the U.S. back in, say, 1999. A descriptive statistic would just tell us, for example, the average salary for educators was, well, quite a bit less than for podiatrists or dentists.
Okay, just a snapshot.
Just a snapshot. Or another one from 1990 looked at unmarried men per 100 unmarried women in different U.S. metro areas.
I remember seeing things like that.
Yeah, you'd see men outnumbered women in Jacksonville, North Carolina, but women greatly outnumbered men down in Sarasota, Florida. Those are just facts about those places at that time.
And sports stats are almost all descriptive, aren't they?
Absolutely. A basketball player's shooting percentage.
Yeah.
Or the winning times for Olympic marathons over 100 years.
Just describing what happened, the facts.
Precisely. Now, the other branch, inferential statistics, this is where we make that big leap.
The leap being generalizing.
Generalizing beyond the data you have to a larger group. A population.
Okay, so if you're working for, let's say, a big news outlet, and you want to know how Americans feel about new voting rules, you can't ask everyone.
Right, you just can't.
Yeah.
So instead, you'd survey a smaller, hopefully carefully chosen group of Americans. That's your sample.
And then use inferential statistics to make an educated guess about the whole the population.
Exactly. And the huge challenge there, of course, is making sure your sample is truly representative.
Because if it's skewed...
Your conclusions are skewed. Like if we wanted to estimate how many math classes college seniors take, but our sample accidentally included way too many math majors.
The results wouldn't reflect all seniors, just the math whizzes.
Precisely. A bad sample leads you way off track, makes your conclusions about the population unreliable.
Got it. Sample, subset, population.
Right.
The whole group. Okay, now, digging deeper. The building blocks, variables, independent versus dependent. How do we tell them apart?
Okay, think of it like this. The independent variable is the one the experimenter manipulates, or chooses. It's what you change or control.
Yeah.
The dependent variable is what you measure as the outcome. It depends on the independent variable.
So like in a drug trial.
Perfect example. If a company is testing a new cancer drug, the independent variable might be drug A, drug B, or placebo. The dependent variable could be tumor size after 6 months or survival rate.
Okay. Or car brake lights.
Yeah, if a manufacturer is testing brake light brightness, brightness is the independent variable. The time it takes a driver behind them to hit their brakes. That's the dependent variable.
And these independent variables can have different levels.
Right, like the drug example had 3 levels, drug A, drug B, placebo. Or you might compare 5 different types of diets. Those are the levels.
Makes sense. And then variables also come in 2 main flavors, qualitative or quantitative. What's the difference for us?
Good question. Qualitative variables, sometimes called categorical, they describe an attribute, a quality, something that doesn't have a natural numerical order.
Like hair color.
Hair color, eye color, religious affiliation, brand of car. The values just differ in kind, not amount.
And quantitative.
Quantitative variables are measured in numbers: height, weight, shoe size, temperature, how many hours you slept.
Okay, and this leads us somewhere important. Levels of measurement. Why does this matter? You said it determines what math you can even do.
Absolutely. This is fundamental. The level of measurement dictates what statistical operations are meaningful. Get this wrong, and you can seriously mislead yourself or others.
Okay, run us through them quickly.
Sure, 4 main types. First, nominal scales. These are just labels, categories with no order.
Like the favorite color example, coding red is 1, blue is 2.
Exactly. Calculating the average favorite color is meaningless. They're just names.
Okay, next.
Second, ordinal scales. Here, there is an order, but the gaps, the intervals between the values, aren't necessarily equal.
Like satisfaction ratings. Very dissatisfied to very satisfied.
Perfect. Very satisfied is better than somewhat satisfied, but is the difference in satisfaction the same as between, say, neutral and somewhat satisfied? Probably not.
Right, the steps aren't equal. What's third?
Third, interval scales. These have ordered values and equal intervals between them. And this is key, no true 0 point.
Fahrenheit temperature. 0 degrees doesn't mean no temperature.
Exactly. It's just an arbitrary point on the scale. So you can say 60 degrees is 10 degrees warmer than 50, but you can't say 60 degrees is twice as hot as 30 degrees.
Ah, okay. That leaves.
Fourth, ratio scales. These have it all. Ordered values, equal intervals, and a true 0 point. 0 means the complete absence of the thing being measured.
Like Kelvin temperature. 0 Kelvin is absolute 0.
Right. Or the amount of money in your pocket. 0 means no money. And $2 is truly twice as much as $1.
Okay, so the big takeaway is you can't just average anything.
You really can't. Forgetting these levels is why you see people averaging, say, pain scores on a 1-10 scale, as if the jump from 1 to 2 is the same amount of pain increase as from 9 to 10.
Which it probably isn't.
Very unlikely. And that kind of misapplication can lead to flawed conclusions everywhere: drug trials, product surveys, you name it. You have to understand what the numbers truly represent.
You can't just crunch numbers without understanding what they truly represent. That really sticks. Okay, so knowing about variables, let's talk pitfalls. Common mistakes when people interpret stats. You really do have to be wary.
Oh, absolutely. One huge one is the third variable problem.
Okay.
This happens when some unmeasured, lurking third variable is actually causing both of the things you're observing. So you mistakenly think A causes B, or B causes A.
Like the classic example, more churches in a city and more crime.
Exactly. It's not that churches cause crime, or vice versa.
It's just that bigger populations lead to both more churches and more crime. The population size is the third variable.
Precisely. Or another famous one from Taiwan in the 70s. They found a positive correlation between using contraception and having electric appliances.
That sounds odd.
Right, but neither caused the other.
Yeah.
The third variable was education level. Higher education influenced both decisions.
So this hammers home that point. Correlation does not equal causation.
It cannot be stressed enough. Drawing causal conclusions without a proper experiment is incredibly risky, often just wrong.
Okay, another pitfall I feel like I see constantly. Just insufficient information. Numbers thrown out without context.
Yes, so important. Someone might say, interracial marriages are up 75% compared to 25 years ago. Sounds huge, right?
Yeah, sounds like a massive shift.
But what if 25 years ago, only, say, 1% of marriages were interracial? That a 75% increase means it's now 1.75%.
Still a tiny fraction. The percentage increase alone was misleading.
Exactly. Without the base rates, the total numbers, the historical context, The raw number or percentage can deceive.
Then there's self-selection bias. This feels like it happens a lot online.
It does. This is when the people who choose to participate in a study or survey are different in some important way from the general population you actually want to understand.
Like those online polls. Vote now on issue X.
Perfect example. The people clicking that link are likely more passionate or have stronger opinions than the average person. Or imagine a study asking for volunteers to discuss their intimate sex lives.
You're probably not getting a representative sample of the whole population there.
Not even close. The people who volunteer are likely different, so you can't generalize their answers to everyone.
Okay. And a really fascinating one. Survivorship bias. Tell us about that.
Yes. This is when you draw conclusions based only on the things that survived or made it into your sample, ignoring everything that didn't.
The classic story is about the World War II planes, right?
That's the one. Statistician Abraham Wald was asked where to put extra armor on bombers. They looked at the returning planes and saw where they had been hit by anti-aircraft fire.
So the obvious thought is, put armor where the bullet holes are.
That was a naive thought, but Wald realized the crucial insight. The planes that didn't return were likely hit in the places where the survivors had no damage.
Because hits in those other areas were fatal.
Exactly. So he recommended reinforcing the areas that were pristine on the returning planes. Brilliant, counterintuitive survivorship bias analysis.
Wow. That's amazing. Okay, one more pitfall. Regression toward the mean. This seems to explain a lot of streaks, hot or cold.
It really does.
Yeah.
It's the phenomenon where if you measure something twice, an extreme score on the first measurement tends to be closer to the average on the second measurement.
Why does that happen?
Think of performance like a test score, or an athlete's game as having two parts, true skill and random chance or luck.
Okay.
An extremely high score often involves unusually good luck. An extremely low score often involves unusually bad luck.
And luck usually doesn't repeat itself to the same extreme degree?
Exactly. So on the remeasurement, the luck component tends to be less extreme, and the score naturally regresses or moves closer back towards the person's true average performance level.
So this is important for studies, right? Like if you study people with really high anxiety scores.
Definitely. Say you select people who scored extremely high on a test anxiety scale. You give them some therapy, then you retest them, and their scores are lower.
You might think, aha, the therapy worked.
But some of that improvement might just be regression to the mean. They were selected because they had an extremely high score, likely due partly to a bad day or bad luck when they took the first test. They probably would have scored a bit lower on a retest anyway, even without the therapy.
So you have to be careful not to confuse the treatment effect with this natural regression effect.
Precisely. It's a fundamental statistical pattern we see everywhere.
Okay, so with all these potential traps in mind, let's talk about visualizing data properly. A good graph can make things clear, but a bad one.
A bad one can seriously mislead. We've all seen basic ones like histograms and frequency polygons.
Right, histograms show the distribution, like how test scores are spread out.
Yeah, they group quantitative data into bins and show how many fall into each bin. Great for seeing the shape of the data. Is it symmetric? Is it skewed, meaning it has a long tail in one direction?
Like seeing if most students scored low or high on a test.
Exactly. Frequency polygons connect the midpoints of those histogram bars, useful for comparing distributions on the same graph.
Okay, what about pie charts and bar charts? They're everywhere, especially in news reports or presentations.
They are common. Pie charts are okay for showing proportions of a whole, but only if you have a small number of categories.
Like maybe what kind of computer people own before buying an iMac?
Something like that.
Sure.
But even then, comparing sizes of slices can be hard for the human eye. The data visualization expert Edward Tufte famously said, "The only worse design than a pie chart is several of them."
Huh. Okay, so use with caution. What about bar charts?
Bar charts are generally more flexible. They're good for comparing frequencies or quantities across different categories, like iMac purchases by previous computer type, or maybe comparing the number of players for different online card games on different days.
But bar charts can be manipulated too, right? What should we watch out for?
Oh, definitely. Two big distortions. First, messing with the bar heights. So the visual difference doesn't actually match the numerical difference, sometimes called the lie factor.
Sneaky.
Very. Second, and maybe more common, is starting the vertical axis, the y-axis, at some value other than 0.
I've seen that. It makes small differences look enormous.
Exactly. It dramatically exaggerates the visual difference. Always check the baseline of a bar chart.
Good tip. And you mentioned line graphs earlier.
Yes, a crucial point.
Yeah.
Only use line graphs when the horizontal axis, the x-axis, represents something with a natural numerical order, like time or age groups or dosage levels.
Not just categories like different brands or different countries listed alphabetically.
Absolutely not. Connecting those points with a line falsely implies a trend or a continuous relationship that doesn't exist.
Yeah.
It's a serious misuse of the graph type.
Got it. Okay, what other visual tools are useful? You mentioned box plots.
Box plots are fantastic. They give you a quick visual summary of a distribution center, spread, and outliers.
How do they work?
They show the median, the middle line in the box, the 25th and 75th percentiles, the edges of the box. This range is the interquartile range, or IQR, and then whiskers that typically extend out to the highest and lowest values within 1.5 times the IQR from the box. Anything beyond the whiskers is marked as a potential outlier.
So you can easily compare the spread and typical values of different groups side by side, like reaction times for men versus women.
Exactly. Very powerful for comparisons and spotting unusual data points.
And line graphs, when used correctly.
When the x-axis is numerical, they're essential for showing trends over time or across ordered categories. Think stock prices, temperature changes over months, things like that. The key is that connection between points means something.
Okay, so visualize carefully, check the axes, use the right chart type. Now, summarizing data with numbers, we often say average, but you mentioned there's more than one kind.
Right, we're talking about measures of central tendency, trying to find the typical or central value in a data set. The most common is the mean.
The arithmetic average. Add them up, divide by how many?
That's the one. It's useful, but it has a weakness. It's very sensitive to extreme scores or outliers.
Like the Bill Gates example. If he moves into a neighborhood, the mean income shoots up, but it doesn't reflect most people's reality.
Exactly. A few very high or very low values can pull the mean way off from the center of the bulk of the data.
So what's a more robust alternative?
The median. This is literally the middle value when you line up all your data points from smallest to largest.
So 50% of the data is below it, 50% is above it.
Precisely. If you have an odd number of data points, it's the one right in the middle. If you have an even number, it's the average of the two middle ones. Because it only cares about the middle position, it's not affected by extreme high or low values.
Much better for skewed data like an income. What about the mode?
The mode is simply the most frequent value that appears in your data set.
Like if you surveyed favorite colors and blue is chosen most often, blue is the mode.
Exactly. It's most useful for categorical data, but can be used for quantitative data too, though a data set might have no mode or multiple modes.
So the takeaway is mean, median, mode. They tell you different things about the center. Choose wisely based on your data.
Absolutely. If you have outliers or skewed data, the median often gives a better sense of the typical value than the mean.
Okay, center covered. Now, how spread out is the data? Variability, dispersion? What are the key measures here?
Right. We need to know if the data points are clustered tightly together or spread far apart. The simplest measure is the range.
Maximum value minus minimum value.
Yep. Easy to calculate, but like the mean, it's very sensitive to outliers. Just one very high or very low value determines the entire range.
So maybe not the most reliable.
Often not. A more robust measure is the interquartile range, or IQR. We touched on this with box plots.
That's the range of the middle 50% of the data.
Exactly. It's the difference between the 75th percentile Q3 and the 25th percentile Q1. Since it ignores the top 25% and bottom 25% of the data, it's not affected by extreme outliers.
Okay, that sounds useful. But the one everyone hears about is standard deviation.
Ah, yes, the standard deviation. And its close relative, the variance.
What's the difference?
Variance is calculated as the average of the squared differences of each score from the mean. Squaring makes all differences positive and emphasizes larger deviations.
Squared differences. That sounds a bit abstract.
It is, units-wise. That's why we usually take the square root of the variance to get the standard deviation.
And that brings it back into the original units of measurement.
Exactly. So if you're measuring height in inches, the standard deviation is also in inches. It represents roughly the typical or average distance of the data points from the mean.
So a small standard deviation means?
Data points are clustered tightly around the mean. Low variability.
And a large standard deviation.
Data points are spread out widely. High variability. It tells you how representative the mean is. If the standard deviation is huge, the mean might not describe any single data point very well.
Got it. That's crucial context for interpreting the mean. Okay, let's shift gears slightly. Probability. You said this is the foundation for inference.
It absolutely is. Understanding probability is essential for understanding how we generalize from samples. There are a few ways to think about what probability even means.
Like flipping a coin.
That's one. Symmetrical outcomes. If you have a situation with several equally likely outcomes, like a fair coin, 12 heads, 12 tails, or a fair die, 16 for each face, the probability is just 1 divided by the number of outcomes.
Okay, what else?
Second, frequency. This is about the long-run proportion. If a weather forecast says a 10% chance, or 0.10 probability of rain, it means that over many days with similar conditions, it would rain on about 10% of them.
So it's based on past occurrences or expected long-term patterns.
Right. And third, there's subjective probability. This reflects personal belief or confidence, like saying, I think there's a 70% chance my team will win tonight. It's based on judgment, not necessarily symmetrical outcomes or long-run frequencies.
Okay, so how do we combine probabilities? What if I want to know the chance of two separate things both happening?
If the events are independent, meaning one happening doesn't change the probability of the other happening, you just multiply their individual probabilities.
Like flipping two coins and getting two heads.
Exactly.
Yeah.
Probability of heads on the first is 12. Probability of heads on the second is 12. They're independent. So the probability of both is 12. 12 equals 14.
And what about the probability of event A or event B happening? Like drawing an ace or a club from a deck?
Good question. For A or B, the inclusive or, meaning A, B, or both, the rule is PA or B plus PB, PA and B.
Why subtract the A and B part?
Because if you just add PA and PB, you've double counted the outcomes where both A and B occur. For the ace or club example, the ace of clubs gets counted in both aces and clubs, so you subtract its probability once.
Makes sense. Now, what if events aren't independent? That sounds like conditional probability.
Exactly. Conditional probability is the probability of event B happening, given that event A has already happened. We write it as PBA.
Like drawing two aces from a deck.
Perfect example. The probability of the first card being an ace is 452. But given you drew an ace, the probability of the second card being an ace is now only 351, because there are fewer aces and fewer cards left. The second event's probability depends on the first.
Okay, this feels like it connects to something you mentioned earlier, interpreting medical tests. Base rates and Bayes' theorem.
Absolutely. Critical connection. This is where many people, even doctors sometimes, get tripped up by probability. Let's talk about base rates.
The underlying frequency of something in the population.
Exactly. Suppose there's a test for a rare disease, disease X, that affects only 1 in 10,000 people. The base rate is very low.
Okay.
Now, imagine a test for this disease is 99% accurate, meaning it correctly identifies 99% of people who have the disease, true positives, and correctly identifies 99% of people who don't have the disease, true negatives. So only 1% false positive rate and a 1% false negative rate.
Sounds like a really good test.
It does. But now, suppose you test positive. What's the probability you actually have disease X? Is it 99%?
My gut reaction is, yeah, close to 99%. But I suspect it's a trick question involving the base rate.
We got it. Because the disease is so rare, even that small 1% false positive rate catches a lot of people relative to the actual number of true cases. Let's think about 1 million people.
Okay.
Only 100 people actually have the disease, 1 in 10,000. The test correctly identifies 99 of them, 99% accuracy.
Okay, 99 true positives.
Now consider the 999,900 people who don't have the disease. The test incorrectly flags 1% of them as positive. That's almost 10,000 people, 9,999 false positives.
Wow. So if you test positive.
If you test positive, you're in a pool of about 99 true positives and 9,999 false positives. Your actual chance of having the disease is 99 divided by 99 plus 99.99, which is less than 1%.
Less than 1%, even with the 99% accurate test.
Yes, because the base rate was so incredibly low. Forgetting the base rate leads to a massive overestimation of your probability. Bayes' theorem is the formal math for combining the test accuracy with the base rate to get the true conditional probability.
That is mind-blowing and incredibly important for interpreting any diagnostic test result or rare event probability.
Hugely important.
Okay.
Okay, so probability underpins inference. Let's talk about the bridge. Sampling distributions.
This sounds complex. What's the core idea?
Imagine you have a population, say, all adult women in Houston.
Yeah.
You want to know their average height. You can't measure everyone.
Right. You take a sample.
Okay, now imagine taking many, many random samples of, say, 100 women each. For each sample, you calculate the mean height.
You'd get slightly different means each time, right? Due to random chance and who got picked.
Exactly. The sampling distribution is the distribution of all those possible sample means. It's a theoretical distribution showing how much sample means are likely to vary just by chance.
Okay. And what does this theoretical distribution look like?
Two key things. First, the mean of this sampling distribution of the mean is actually equal to the true population mean. On average, the sample means center around the right value.
It's good, unbiased.
Yes. Second, and crucially, the variability or spread of this sampling distribution gets smaller as your sample size n gets larger.
Ah, so bigger samples give means that are more tightly clustered around the true population mean.
Precisely. The standard deviation of the sampling distribution, called the standard error, decreases as n increases. This is why larger samples give you more precise estimates of the population parameter.
And this connects to the central limit theorem.
It does. The central limit theorem tells us that even if the original population data isn't normally distributed, bell-shaped, the sampling distribution of the mean will tend towards a normal distribution as the sample size gets large enough. This is incredibly powerful because it allows us to use the properties of the normal distribution for inference.
So bigger samples and more reliable estimates, and the distribution of those estimates becomes predictable.
You've got it. That's the foundation for generalizing from sample to population.
Okay, building right on that. Estimation and confidence intervals. What's a point estimate again?
A point estimate is just your single best guess for a population parameter based on your sample data, like using your sample mean height as your estimate for the population mean height.
But it's just one number. It doesn't tell you how uncertain you are.
Exactly. That's where confidence intervals come in. They provide a range of values that you're reasonably confident contains the true population parameter.
Like the margin of error you hear in polls?
Precisely. If a poll says 55% support candidate A with a 95% confidence interval of plus minus 3%, it means the interval from 52% to 58% was constructed using a method that, if repeated many times, would capture the true population proportion 95% of the time.
So it gives a sense of the precision of the estimate.
Yes. A narrower interval means a more precise estimate, usually due to a larger sample size or less variability, while a wider interval indicates more uncertainty.
And I've heard the terms bias and precision used when talking about estimates.
Right. An estimate is unbiased if its sampling distribution is centered on the true population parameter. It doesn't systematically overestimate or underestimate.
Okay. And precision.
Precision refers to the spread of the sampling distribution. A more precise estimate has less variability. Its standard error is smaller. You want estimates that are both unbiased, accurate on average, and precise, low variability.
Got it. Accurate and reliable. Okay. We estimate parameters. Now, how do we use data to make actual decisions? This brings us to significance testing. You said this is often misunderstood.
Hugely misunderstood. Significance testing is all about challenging a specific hypothesis called the null hypothesis, H0.
The null hypothesis is usually the assumption of no effect.
Typically, yes. It's the default assumption. For example, H0 might state that the difference between the mean recovery time for patients getting a new drug versus a placebo is 0, or that the correlation between two variables is 0. Researchers usually want to find evidence against the null hypothesis.
And they do this using the p-value.
Correct. The p-value is calculated based on your sample data. It tells you the probability of observing a result as extreme as, or more extreme than, what you actually got if the null hypothesis were true.
So a really small p-value means...
A really small p-value, say less than 0.05, means your observed result would be very surprising, very unlikely, if there were truly no effect, if H0 were true. This leads you to doubt the null hypothesis.
And that 0.05 threshold is the alpha level.
Exactly. The alpha level or significance level is the cutoff you decide on before you do the test. If p-yadi, you reject the null hypothesis and declare the result statistically significant.
Okay, now the crucial point. Statistical significance versus practical significance. These are not the same thing.
Not at all. This is maybe the biggest misconception. Statistical significance just means you have enough evidence to say the effect is likely not exactly 0. It does not automatically mean the effect is large, important, or meaningful in the real world.
So you could have a tiny, practically irrelevant effect be statistically significant if your sample size is massive.
Absolutely. A drug could lower blood pressure by a statistically significant but clinically meaningless 0.1 points if tested on millions of people. Don't equate significant with important.
Okay, and errors can happen here. Type I and type 2.
Yes. A type I error is rejecting the null hypothesis when it's actually true. A false positive. Finding an effect that isn't really there. The probability of making a type I error is controlled by your alpha level.
So if alpha is 0.05, you have a 5% chance of a type I error.
Correct, assuming the null is true. A type 2 error is failing to reject the null hypothesis when it's actually false. A miss. failing to detect an effect that is really there.
And one more big misconception. If a result is not statistically significant, you should not conclude that the null hypothesis is true.
Absolutely critical. You never accept the null hypothesis. A non-significant result simply means you didn't find sufficient evidence to reject it. The study might have been underpowered, too small a sample, or the effect might be real but small. It's inconclusive.
Like the James Bond martini example. He gets 10 out of 16 right, p 1.62. Non-significant. Doesn't prove he's guessing.
Exactly. It just means this particular experiment didn't provide strong enough evidence to conclude he's better than chance, even if he truly is slightly better. Non-significance means we can't tell from this data, not there is no effect.
That changes everything about reading study results. Okay, moving beyond just detecting an effect, how do we measure its size? Effect size.
Yes, effect size quantifies the magnitude of the effect. How big is the difference? How strong is the relationship? It complements significance testing.
So for comparing means, like drug versus placebo.
A common measure is Cohen's d. It expresses the difference between two means in terms of standard deviation units. So a d of 0.5 means the group means are half a standard deviation apart. This makes it scale-free, easier to compare across different studies or measures.
And even a small effect size, statistically speaking, could be practically important.
Definitely. Context is everything. Cohen suggested benchmarks, d equal 0.2 small, 0.5 medium, 0.8 large. But a small d of 0.2 could be hugely important in some contexts.
Like selecting students for a program.
Right. If a selection test shows a small average difference between two groups, d is 0.2, but the cutoff score for admission is high, that small difference could dramatically change the proportion of selected students from each group. A seemingly small effect can have big practical consequences depending on the situation. Always ask how big and does it matter in this context?
So, wow, we've really covered a lot of ground today.
We certainly have.
From the absolute basics, descriptive versus inferential, to variables, levels of measurement.
Then spotting those common pitfalls like third variables and survivorship bias.
Visualizing data carefully, understanding averages and spread.
The fundamentals of probability, base rates, sampling distributions.
And finally, significance testing versus effect size, making decisions but also understanding the magnitude.
The whole goal here really was to equip you, to help you become a more intelligent, more critical consumer of all this statistical information flying around.
To look beyond the headlines, question the numbers.
Exactly, to ask those deeper questions.
So, the final thought for everyone listening. After today's deep dive, what facts and figures will you look at differently? What new questions will pop into your head the next time you see a percentage in an ad or a finding in a news report?
Because ultimately, this isn't just about numbers. It's about understanding the world more clearly.
Seeing the story behind the data. A crucial skill for everyone.